Professor Pevný, if you are ready, the floor is yours.
Thank you very much for the introduction. Good afternoon. I would like to talk about a method that I had in mind something like 10 years, and it really took us 10 years to make it work, and because it was done by our PhD student, I really love it. So let me start with an introduction, because it's about steganography, and the steganography it's not very widely known topic. So the steganography is typically introduced using something called prisoner's problem. The story goes that we have two prisoners. One is Alice, the other one is Bob. They want to plan an escape from the prison. They are allowed to exchange messages, but all messages are intercepted by warden, typically called Eve. And if Eve sees something suspicious, she will stop the communication and their plan is effectively ruined. So many of you would think that, okay, well, maybe Alice and Bob can use cryptography, but if they use cryptography, their exchange message would look like this, and it's immediately visible that Alice and Bob wants to hide something, and and Eve will be warned, and she will stop the communication, and that's why they will use steganography. And one example can look like this: my dear is Bob, let me share some music that I have written, and tell me what do you think about it. And there would be a piece of attached music, which looks perfectly normal, but because Bob has a shared key with her, he knows that the notes which are raised or lowered carries the message, and the position and the type of note. With that she can decode and read the message, whereas Alice can't do that. And this is, of course, very naive, and we need a proper definition of the steganographic security. So let me just spend a little bit more time on that. And that's really important to be able to very well assess under rigid conditions the security of the scheme. So we will be talking about steganography by cover modification. We assume that there is some probability distribution of objects without message. We will call them cover, and for us it's typically digital images. Then there will be some probability distribution of the messages that will be hidden inside those cover objects. We typically assume that it's just a random bitstream, because every sane Alice would encrypt the message. And then we assume that there is some probability distribution over keys, and that key is shared between Alice and Bob. So there is nothing similar to asymmetric steganography, it's always symmetric. And then there is an embedding function. That embedding function takes a cover object's message and key and produces a stego object that is sent to Bob. Bob uses his extraction function together with key, reads the message. And important for the development of the field is that Eve has complete knowledge of the scheme. She knows the distributions, if they are possible to be known. So she knows distribution of covers, messages, keys. She knows all the details how embedding function is implemented. She just doesn't know the realizations that led to creation of a possible stego object. And with that, this helps us to define the security of the steganographic algorithm, which is some distance between probability distributions of cover objects and stego objects. So I prefer total variation, but other distances on probability measures are possible. And this sort of setting is called Kerckhoffs principle, and it's used, for example, in cryptography, where you are assessing a quality of the cryptographic algorithm. You assume that your adversary knows everything except the shared key, right? Because otherwise, it's security by obscurity, and it doesn't really work well in practice. Okay, so who is using steganography? Well, obviously, it's used by dissidents and spies. So I would like to just mention that there is a lot of discussion about some surveillance schemes like chat control or APR-CSAM. So I would assume that once this is widely deployed, the steganography is going to be used way more often, because it's going to be absolutely immune to this surveillance scheme. We know that it has been used by terrorists in the past, and we know that it's used by malware. So that's sort of how it's used. So let me now give you an example of steganography, which was kind of state-of-the-art at the time when I was doing Ph.D., and it's in digital images. So we assume that we want to hide some message. The message is binary. The message is these 5 blue bits. And we will hide the message into least significant bits of every pixel. We assume grayscale images, so there will be 1 bit per pixel. And we will visit the pixels in the order that will be determined by a shared key. And if the least significant bit of that pixel doesn't match the bit of the message, we will just overwrite it. Right? So, for example, this pixel before had the value 204, and now it has value 205. And this change is so tiny that the human eye can't see it in normal covers. But of course, it's very detectable. If we just look at the least significant bits, there is some local correlation, and if I will embed message which is going to be equal to the number of pixels, I will just destroy the correlation, and it's a very detectable algorithm nowadays, because this local correlation is destroyed. So we need to do something better. So let me just now formulate the problem. Like the problem of steganography and steganalysis is just defined by the 2 parties. That is the Alice, who wants to design as secure algorithm as possible, and there is an Eve, and she wants to design as better detector as possible. And that's classic in most security schemes. And therefore, if you look in the history of the field, these two researchers or 2 groups of researchers are constantly fighting each other. Right? And honestly, it's very fun to play for a few years, but then you sort of get tired. And I think the fundamental question is, if it is possible to break this cycle, right? Is it possible to derive an algorithm, and I'm specifically interested in Alice. My question was, can I design an algorithm such that when I know the class of detectors that Eve will use, I will optimize the algorithm, the steganographic algorithm, to be as secure as possible? So that was my question. Okay, so how we do it? If we look at the problem, there is clearly a game, so we should formulate the problem using concepts of game theory. So we have 2 players, Alice and Eve, they have antagonistic goals. We assume 0 sum. So what we took was a min-max solution concept, and it nicely corresponds to Kerckhoff's principle. So we assume that there is some space of embedding functions, call it E, and there is a space of detectors, call it calligraphic F. And what Alice wants to do, she wants to pick a detector such that when, Alice wants to pick an embedding function such that when Eve picks her detector, the error of the detector is as high as possible. Right? And it's important that Alice is picking first. Right? So she is committing algorithm, she is making that algorithm public, and once she makes that public, Eve can do the best she can to make it as detectable as possible. And of course, this game seems horrible to optimize, particularly because, well, there is some F, which is space of all detectors, and think about like space of all convolution neural networks with all possible weights of all possible architectures. So effectively, infinite space. And then we need to somehow enumerate the space of embedding functions. So the way to solve these problems in game theory is to use double oracle algorithm. And what the double oracle algorithm does is that it will perform iterations, and in each iteration, Alice would first create a steganographic algorithm that's going to be maximally secure with respect to detectors that Eve has created in previous iterations. So the maximization here is performed over a finite set of detectors and therefore possible. There is no longer infinite set, there is just a finite set over a small number of detectors. And once she designed her algorithm, Eve creates a new detector, which is best with respect to the Eddie's new algorithm. And this sort of alternates, and it's known that it, under some circumstances, converge to the min-max saddle point. What was good that, with the nascent of the convolutional neural networks, the step 2, the step 2 is trivial nowadays. The step 2 means train neural network with some architecture. Usually the architectures are taken from the computer vision. So this is trivial problem. The real problem was how to design the new steganographic algorithm. And that's what effectively our work was about. So before going that, I will give you sort of a background how the steganography works, or modern steganography. And modern means like post-2010. That's called modern. Right? The modern steganography is using something which is called steganography by distortion minimization. We assume that we have some function, here is denoted by fds, which for given cover image measures the distortion. And the distortion is something like detectability. So if I create a stego object, this function should tell me how much detectable I am. And I will pick a stego object such that when I extract the message, it codes the message that I want. So this is pretty general. It's very well written. The problem is that we can't really use this in practice because it's NP-complete problem. Right? We don't really have an efficient scheme how to optimize this. But what we have instead, we have efficient algorithms that can do it for a linear case. So the distortion function needs to be linear. It's like a sum of, we call it additive distortion function from historical reason. And what it means in practice, if I change one pixel, it doesn't affect the cost of changing other pixels. The costs are independent, they are just added. And the decoder is linear. It's linear here. The decoder is linear over like modulo algebra. And we have algorithm which optimizes this very efficiently using Viterbi algorithm. So that's what we know. And what we also know, we can simulate the optimal embedding. So if we assume that our distortion function is linear, so we still have the linear distortion function, and we know that we want to communicate a message of length m, so the messages are not so lengths, we know that each pixel would be changed with certain probability, which is given by this Gibbs distribution, and this lambda here is determined by this entropy constraint. And this is important. So for this linear distortion function, we can effectively embed and we can effectively simulate the embedding. And the simulation was very important because it allows the field never release a working algorithm. So the field very, very rarely releases working algorithm because it's sufficient to release the simulator because the real embedding is very close to it. And the second important consequence is that when we are designing a new steganographic algorithm nowadays, it's just sufficient to design the additive distortion function, this linear cost. And this is something we did first in 2010, where we put all these blocks together. And the effect of our distortion function is that when I visualize the probability that a pixel is going to be changed during hiding the image, during embedding of the message, the steganographic scheme will primarily change pixels around edges and in highly textured areas. And it's because those parts are way more difficult to model, and therefore the changes there are way less detectable. And of course, if I will increase the message, I am taking from the algorithm a space for optimization, and the algorithm will start to take the kind of more detectable areas. Right, so this is what we done in 2010, which is like 15 years. Right? And I saw that it's more or less end of the steganography. I saw that designing the steganographic function, this additive distortion function is going to be trivial, but it has proved not to be trivial. There were a few of them that were released, but to my surprise, most of them were designed by heuristical methods. It was not that they would take the existing detecting methods for detecting steganography and got inspired. It was just, well, I believe that textured areas are difficult to model, so let's somehow model textured areas and detect them. Okay, so now I will present the core part of our work, which is trivial. So the problem that we have is that we know that distortion functions has to be non-additive, right? Because distortion function can be, for example, convolution neural network, and that's everything but additive. But the problem is that effective coding or sampling exists only for additive distortion functions. Right? So we somehow need to do something which will get us to the additive space. And the idea was, on the end, very simple. What we said that, okay, let's, for a fixed image, so someone gave me image into which I want to hide the message, I will optimize the coefficients of the additive distortion function such that when I create the stego object, it's going to be minimizing the distortion measured by the non-additive distortion function. So the idea here is similar to something like mean field methods from physics or variational method from statistics, when we have some very complicated probability distribution functions, and we approximate it by, let's say, product of independent probability distribution functions. So it's a very similar problem. So when I write it in like math, what we needed to do was to find coefficients of this additive distortion function, such that when I will sample stego objects from the simulator, it's gonna minimize the non-additive distortion function. And this formulation, we want to optimize the coefficients using gradient descent, because otherwise we can't do it with zero-order methods. We need to use first-order optimization methods, otherwise we are never able to compute it. And there are two problems that we had to overcome. The first one is that the stego objects are discrete. So we are optimizing parameters of discrete probability distribution functions, which typically is non-trivial. But thanks to the progress in machine learning, mainly in years 2016 and 2017, it was possible. And then we need to take into account the entropy constraint. And that was made possible using gradient of implicit function. So that was, on the end, relatively trivial. Okay, so let me show you how it works in practice. And before I show you the concrete results, I will explain you how to read them. So I told you that the algorithm is iterative. It's double oracle algorithm. In every iteration, each part creates a new Alice is creating a new embedding function, and Eve is trying to find the best detector. So on x-axis is going to be the iterations of the double oracle algorithm. We jump-started the optimization by the state-of-the-art. So the state-of-the-art is at the iteration 0. And we want to force Eve to make as many errors as possible. So the higher we go, the better we are. And we make the protocol more interesting because, when Alice is designing her steganographic algorithm, she doesn't have to have a complete knowledge of detectors that Eve might create. And therefore, we assumed that Alice will know 3 steganalitic algorithms, which are just different variants of the convolution neural networks. And Eve would use the same 3 types of neural networks, but then she will use additional detectors that are based on features and linear classifier, which was what the field was doing before the year 2015. So the state of the art when we started was something like 5 or 6% error rate. And as the algorithm was progressing, the Alice was becoming progressively better and better. And when we stopped it, she was something like 37, or Eve was making 37% of error. And just to give you kind of sense of what is progress in the field, like improvement by 1% would probably give you conference publication, improvement by 3% would probably give you journal publication, and we improved by 30%. Right? So it was something eye-opening. With that, I will conclude my talk. I have to say that it would never realize if we didn't have any RCI funding, because it's very computationally intensive algorithm, and we had to use it. I'm still honestly not very satisfied with it. There was something that you might miss, but when we are optimizing, we are conditioning on the cover image, but we are optimizing with respect to all possible messages, which is clearly not correct, because when Alice is optimizing the embedding, when she is optimizing the cost, she can take the message into the account. It makes the problem way more complicated, but I think there is a solution. And also, as I said, it's super slow. Like it was like the whole PhD of that student was something like 200,000 GPU hours at that time. But it leads to, I think, very interesting result. And that concludes my talk. Thank you very much for attention.
Thank you very much for the introduction of the topic, which probably have always been topical during rivalry of superpower countries. And now I open the public discussion and ask for questions. Professor Kittler.
Thank you very much for your talk. You focus on sort of conflict between hiding and detection.
Mm-hmm. But I'm interested in the hiding.
Okay, but to prevent the message having impact, would it be easy to distort?
Yeah. Yes.
So
yes, it's
is
trivial.
that a possibility for Eve?
So this is very trivial. Like these schemes are, very sensitive to changing pixels, but like we would need to. Possibly there is a way how to make it robust. We would need to know the source of robustness. Like to sort of know how the distortion might look like. It's become increasingly more researched, but we wanted to do this in kind of laboratory conditions, right? And that's typically, by the way, like where the research is. It's very laboratory.
Thank you.
Professor Svoboda and then Professor Hamhalter.
afraid I didn't catch all the details. If you may go one slide back, I'm still kind of replaying in
this one or this one?
The next one. I'm still thinking about the limitations you mentioned, so I'm still kind of
what's
the input? So does it mean that that Alice needs to do the double oracle game for each possible message, or how?
No. So when it's here. So when Alice is hiding, she will get the cover image, which is that X, and she needs to perform this optimization, and this distortion function is those set of detectors that were created by the double oracle algorithm. Right, so she needs to perform this optimization before she can embed, because this optimization gave her this C, this cost, which defines the cost of changing pixels. So the C is the additive distortion function, and this FDs is now set of detectors that were created during the double oracle algorithm.
Okay, so the distortion functions are independent on the how to say in English, on the carrier of the message. Okay.
So they are optimized for certain class, for certain probability distribution of the carriers.
Thank you.
Professor Hamhalter, then Professor Matas.
In your scheme, do you consider only discrete random variables, meaning having finite or countable many values, or you are also dealing, or it's possible, I mean, to deal with some continuous function using more analytic methods and so on?
Thank you. So this is good question. Good question. So we are dealing with discrete because it was created for digital images, and we know that we need to treat pixels as a discrete variables, because on the end you need to send them, so they will be stored as bytes.
Yes.
Right. So we need to be discrete.
Okay. Thank you.
Now, Professor maybe Professor Železný is closer.
Is it my turn?
Yes, it's your turn.
So I only understood from implicitly that this method assumes that the content where you embed is pictures, images.
Well, it's completely general.
All the examples were.
Well, we do typically just images. Like that's how the field works.
Okay. So how would you define the scope of content that is eligible?
What do you mean, like content? I mean, like
images,
object.
There were,
so audio would so audio would be relatively easy. Audio is easy.
So maybe everything that you can represent as a series of bits.
I mean, like it goes into hairy details, right? Because like images are relatively easy because you can do them in the spatial, and if they are compressed in JPEG compression, the JPEG compression is trivial. It's very easy, and that's why we typically work with digital images. Audio is similarly easy. In general, it can be used for video, but the steganography in video is complicated because the codec in video is quite non-trivial. And I think the field doesn't have a good knowledge of the dependencies in the video. Right.
Okay, so these considerations that you are mentioning now, that's something that may need a little more clarity, right? Because as a potential user, I may legitimately ask the question: so, which kind of content is good?
You mean which kind of media is good carrier for the steganography?
Yeah.
So I would definitely pick digital images because they are the most researched and they offer very good ratio of capacity with respect to the size. Audio is very heavily compressed and video is very heavily compressed, and in video I would be afraid that if I use it, we don't have as I said, we don't have a good knowledge of the dependencies caused by the codec, right? So there are some, especially Chinese researchers are slightly active in the steganography in video, but the schemes are, to my taste, very naive.
But, so you might go ahead with a definition of the kind like any kind of content where random variations are not destructive or something like that. But
yeah, but it's sort of difficult to define, I would say.
My question was triggered by Joseph Kittler's question, which I'm not sure I understood. So if we go to slide 1, or in the setting of the game, somehow...
Slide 1, okay.
Maybe 2, when you have the... Yeah, maybe when you are explaining
here.
This thing. So I think the idea is that what Alice prepares has to be sent to Bob. But maybe Eve can say, well, you have no reason to... I'm not... Well, you can communicate, but I will do resize by a random factor and do by
that's possible. That's possible. Like it's
so, do people do this type of thing? And I think, am I correct that this is not in the game you are
Yeah. So this is related to someone asked. This is people are increasingly more doing this. It's like robust steganography. And the reason is that people are sharing images through channels which are recompressing, like Facebook, Flickr.
Even adversarial setting, like I am Eve, I can say, well, you can send some image, but I'll do something to it that I'm not telling you. Well, if you are sending a picture of a cow, Bob will see a cow, but I will distort.
You mean that Eve would be active?
Eve will be active, and it does some sort of deformation, because I have no reason to guarantee to Alice that she can send every bit to Bob. He can send an image, but I will play with the image a little bit to make life super difficult for Alice and Bob, and maybe I kill the game.
It has never been done. I mean, it's typically not considered. So the steganography, as is studied, is usually fragile. It's become more and more common because, as I said, like the manipulations are happening. And the reason why it was not studied was that it was usually assumed that it's going to be the field of watermarking, where the watermarking was always assuming that there is an adversary which is trying to remove the watermark. And that's why the steganography sort of, show it under the rug. Right? And, just like watermarking, even in the 90s, they had schemes which survived print and scam attack, where you have been, like, for example, cropping, resizing. But to my knowledge, usually you have to restrict cells to some type of, degradations. You can't be completely immune. And it's very computationally expensive because, for example, if you move the image, if you chop it, you need to register.
Okay, so I was a lot skeptical that when I saw the first results of steganography, I thought this is lost. Like, how can you detect it? But now I'm sort of more optimistic that if you force maybe some providers like WhatsApp that share images to do some sort of little bit of random deformation that nobody would even notice, then the usability of this source for sharing information.
So we are starting to work on that with my colleagues. So they had, and the way our thoughts are sort of going is that it really depends how much knowledge you have about the robustness, about the distortion. So, for example, if it would be Facebook algorithm, we would probably get a good sense how Facebook would work. But as you said, if it's going to be random, it will, change the game substantially.
Yeah, of course, it's like, I just want to make it computationally expensive for you to hide the bits.
Yes.
Thank you.
Or you will decrease the capacity, the usable capacity.
Thank you. So if there are no any other questions, let me thank you again, both lecturers and you, the audience, for questions, and I close the lecture, both lecture sessions.